Good. So today is March 1st, 2022, and we are solving some problems using Gauss's law. So far we have used Gauss's law to calculate the electric field of a point charge and the electric field of the uniform spherical distribution of charges. The next step would be to find out the electric field of a spherical shell of radius r. Okay, so if you did for the point charge and if you did for the uniform spherical distribution, it's going to be rather straightforward to do that for the shell. Okay, so all you have to recognize is that, gotta put the axis, right? X, Y, and Z axis. Don't forget we have a radius r. Go ahead and do your Gaussian surface inside the sphere first. Okay. And, this Gaussian surface encloses a net charge equal to 0. Okay? That's what it does. So that integral that you saw seeing there, that you saw that we're using before, here you go. Let's get the integral here. To enclose, here you go, this integral here. And let's put here a spherical shell. Now I'm gonna do a spherical shell of charge Q. So we're gonna do that now. Here you go. Of charge Q and radius big R. So first we do y, I, r less than big R. Less than big R. For r less than big R, the Q enclosed is what? Is 0. Okay, and oops, because the Q enclosed is 0, here we go, we have this relationship here. We can, okay, we have to look at the integral. E dot dA. Here is the area of the Gaussian surface. The area of the Gaussian surface is different of 0. If the area of the Gaussian surface is different of 0, it means that the electric field must be 0. Okay, so here you go. So for the case that we have no charges inside the Gaussian surface, the electric field gotta be 0. This implies that the E field is equal to 0. Then we can go outside the spherical shell. That's R greater than big R. Okay, R greater than big R is similar to the case of a point charge. Here you go. The charge enclosed is going to be Q. Okay, the problem has spherical symmetry, so we can expect, here you go, the problem has a spherical symmetry, so we can expect that the electric magnitude of the electric field here at this spot is equal to the magnitude here, and so on. And the problem is solved just like the one for the point charge. The point charge or the the sphere with uniform charge distribution. Either one. Let's see here. Like that. And I'm gonna write that down at E equal to KQ KQ over R squared. Like that. I'm not going to put I'll take this one out. Okay, that's the next problem that we are going to do is the problem of the infinitely long rod, charged rod. We start with a rod, put a charge Q on this rod, and I put a row here. A row should be lambda. Yeah, let's see. I may have a reason why I did that. Let's see. The notation we usually use a lambda for spherical shell. Example. I'm going to find this field rod. Okay. Yeah, we're gonna use lambda. I do not know why I use that row here. Here you go. Let's use lambda here. Lambda. Uniform. Okay. Next one is uniform linear charge distribution. Infinitely long rod. Infinitely long rod with a uniform charge distribution. So this one should be case number 4. Okay, here you go. I'm gonna put here. Easily long rod. So this one here, what that we did, is spherical shell. Okay. Infinitely long rod. Okay. Uniform charge distribution. We represent the uniform charge distribution with the Greek letter lambda. This problem is a little bit more difficult. Problems that have spherical symmetry are easier to solve, but this problem here doesn't have spherical symmetry. This problem has cylindrical symmetry, not spherical. Okay, so here you go. So we can set up the x and y axis. Okay. Huh. Yeah. I'm gonna put this one here so it can look better. The previous one, here you go. No x-axis, right? You start with the rod first. Put a label of charge Q in the rod. Set a, don't forget that the rod also has uniform charge density, that I call it lambda, and has an x-axis. x-axis and an y-axis. Okay, so here you go. Here's the observer, right? The observer is looking along the axis of the rod. If you're looking along the axis of the rod, it's going to look like something like that. With the y-axis here, the z-axis here, and the x-axis coming out of the board. Here you go. Like that. So because this situation here has cylindrical symmetry, I can draw my Gaussian surface around the axis of this rod. What you have here is a cylindrical surface, okay, of radius r, by the way. And if it has cylindrical surface, it's reasonable to assume, it's reasonable to recognize that electric field lines are going to extend radially, from the rod. If you look along the axis of the rod, it's going to look just like that, okay? But if you look along the z-axis, the same surface that you saw before is going to be a cylindrical surface. A better way to design to draw it would be a cylinder here. Okay, I put this as a rectangle, but consider that as a cylinder. Picture that as a cylinder. The best way to draw something like that is use a cylinder that we have here in the, let me see if I can find. Here you go. Here's the cylinder. I'm gonna get this guy here. Rotate the cylinder. Okay. That would be the best way of drawing it. A cylinder of radius r. Let's see if I can get it. Replaced by this line that you see. Okay, so here you go. I gotta make this guy transparent. No fill. Yeah, better. And the edges of the cylinder is going to be black. I can put some dashes at it. Yep. And then I remove this square. Now we have something that's more like of a, and the cylinder doesn't have to be infinitely long. It can be finite. Let's see if I have anything else in the next slide. Can you picture that? So you can either have this cylinder, we can look at the cylinder from the along the x-axis, or we can look at the cylinder along the z-axis. Okay, and now I'm gonna copy this cylinder here. Now that I got a better cylinder, here you go. I can remove this guy right in here. Here you go. Cylinders of radius r. Okay, my Gaussian surface. The key here is to find out what would be the proper surface to solve each of those problems. Okay, so here you go. Here are the electric field lines going out of the rod. Okay, those electric field lines have cylindrical symmetry. Let me get this other one here. Okay. And now I'm going to start solving this problem. I drew a different cylinder here. Here the electric field lines. And here what you see, the blue vectors, they are the area vectors. I didn't label them, right? Let me label those area vectors here. Where's my area vector? I don't see my, oh yeah, where's my area vector? Okay, finally, I got it. I'm gonna put the area vector here with the blue color, so you can associate this area vector with what you see there. And I'm gonna make it larger as well. Here you go. I made my area vector without the arrow, right? But I prefer this one here. Each of those blue arrows is an area vector. So here you go. Electric fields, right? And I'm gonna duplicate this slide, and what I have here, I'm gonna show you guys soon what that is. Don't want to overwhelm you with too many drawings, right? Too much information there. So let's oh, here you go, my A, almost invisible. Here you go. So let's go through that again. Here you go. We start with a rod. Start with a rod. This rod has an electric charge. This electric charge is uniformly distributed through the rod. This rod is positioned along the x-axis. And we have the y-axis as well. We want to find the electric field around this rod. Okay? First, we look at the rod along the x-axis, along its axis. When you look at the rod along its axis, it's going to look just like that. The rod is right in here. Okay? With the charge q and uniform charge density lambda, that is dq dx. If q is greater than 0, we should expect that the electric fields are going to point away from the rod. So we go ahead, construct our Gaussian surface first, right? Our Gaussian surface has radius r, and the electric field point away from the rod. Uniform distribution, then it's reasonable to assume something like that. If we look on the other direction along the z-axis, that Gaussian surface that I depicted here before, right, is going to look like a cylinder. And I'm going to change the color of the cylinder so to be consistent with the color that we had before. Here you go, right? And I'm going to increase the size of those lines too, so there is no doubt that those are the same. Let's see, this one better, right? Let's see how it looks like. Yeah, let me see if this guy is too big compared to the other one. Yeah, it's big, a little bit bigger. Let me shrink a little bit. My cylinder is going to be consistent with this with this circle there, right? So here you go. Make it Perfect, right? Here you go. Now I have to replace the other cylinders. Here you go. The radius now became a little bit shorter. I'm gonna shrink this radius. Okay. Delete this guy. Right. So looking from this other angle, the electric fields look just like that, pointing away, pointing the vertical direction, upwards and downwards. Oops. Let's see here. Like I said, I like to get my drawings perfect. So very clear echo. Not only we have an electric field pointing in the polar direction, but we also have an area vector that also points in the polar direction. In the next slide, what we have, let's see here. We have the surfaces. I'm going to start to label the surfaces of the cylinder, so I can come up with a proper derivation. I'm going to do the following too. Even I'm going to do the following. Let's go. Yeah, I'm going to preserve this little circle that you see there because I'm going to need it. I already have a circle on the right side, right? So let's use this circle here on the left side. Here you go. So this cylinder has three surfaces. The first surface is the cylindrical surface itself, okay? That's the first surface. Let's see here. The next surface are the caps. Okay, here you go. First surface. I don't need. Let me get another one here. Okay, the first surface is the larger cylindrical surface that surrounds the axis, and I label it 1. The other two surfaces are the caps. Cap 2 or surface 2 and cap, surface 3. Surface 3. Here you go. Okay, I don't need that anymore. Let's see, I don't need that. Okay. And what is next? We have to recognize that there are two other surface vectors. Because we have three surfaces, we have to recognize that there are other two surface vectors. Here you go. The first surface vector, let me see here. I'm going to label it A1, okay? Let's put it this way here. This guy here is going to be A1 to distinguish from the others. A1, A1. The other surface vectors are going to be A2 and then A3. Oops. Here you go. I have A2. I'm going to replace it with this one here. And I'm gonna have A3. Here you go. What else am I going to do? I am going to make the length of the cylinder equal to length L. Lots of information. Sometimes it's difficult to understand, not because it's mathematically difficult, not because the idea is difficult, but because we have lots of information. Okay? Here you go. I'm going to get this surface right in here. And I'm going to paste it there, my surface number 3. Right in here. Surface number 2 is already here. Those vector areas, they always point away from the surface, from the closed surface, and not towards. Okay? Here you go. Now, what else do we need? I don't think I need that. That's 1D rod. The only thing I added here was 1D rod. All right, so here you go. One D rod. Are you getting the picture? And now we are going to break down our integral in terms of those 3 surfaces. I don't need this drawing anymore. Okay. Using this drawing that you see right in here, I'm going to break down my integrals into 3 integrals. So here you go. This one, not this one here. Always start with with Gauss's law. Always start with Gauss's law. Here you go. Q enclosed. What's the Q that's enclosed? Okay, the Q that's enclosed is going to be what? Is going to be the lambda. Oops, I didn't go. Keep go. Lambda L. Dq dx is equal to lambda. Okay, we want to find the enclosed charge. So the enclosed charge is going to be lambda L. Right? So the right side, we know the right side. And now we're going to break down the left side. There's nothing else we can do with the right side. Let's see what we can do with the left side. Okay, the left side. Remember, we're talking about three surfaces. Now we broke down our single surface into three separate surfaces. Okay, the first surface is going to be an open surface. Our closed surface can be broken down into three separate open surfaces. Here you go, like that. Here is going to be surface 1. Here going to be surface 2. Here is going to be surface 3. Each right in there. I don't need this queue enclosed anymore, right? Just like before, the electric field. Oh, wait a minute. Let's go for our first surface now. This is my first surface. In the first surface, the electric field is parallel to the area vector. Okay? So we go ahead, write that down in terms of the magnitude. We go like that. And we also get the magnitude of the vector area. Like that. And I'm going to emphasize that is the electric field at the surface 1. I'm going to emphasize that. We do the same for the other two. But I emphasize that we are talking about the surface, the electric field at the surface 2, the electric field at the surface 3. Actually, the integral already states that, so in a way it's kind of redundant to write that. I don't need this guy anymore. The electric field at the surface, the magnitude of the electric field at surface number 1 has the same value. So it can be taken out of the integral. By the way, I made a mistake here. Let me correct myself. Okay. Here you go. What's happening here? This integral here is surface number 2. The integral here, the surface number 2, is the electric field dot this A. Okay? Look at the angle between the electric field and the area vector here at the surface. It's 90 degrees, right? So that dot product makes this integrand equal to 0. So I'm going to put that 0. Here's the same thing. Take a look. The surface number 3, electric field 90 degrees with area vector. So what we end up getting is that this third integral is also 0. And we are left only with the first integral. I can take it out. And now we're left with calculating the area of that cylindrical surface. The area of that cylindrical surface is going to be what? It's going to be 2 pi r. Okay, going back to the drawing again. The area of the cylindrical surface is going to be the circumference, 2 pi r, times the length L. Okay, the length L we do not know, but it doesn't matter whether we know or not. In many physics problems, we end up getting, unknown values that ends up canceling out. See that? The L here is going to cancel out to this L. And then we finally get a final result that is Very similar to what actually is the same result, right? That we got before when we calculate. Here you go. The L cancels out with the L. Let me go. Let's do like that. Here you go. L cancels out with L. Then let's see if I can place that in a better way. I'm gonna put the R separately here. Okay, I will take this one out, put it here, and no R anymore. Lambda over epsilon naught. I can do it even better. We usually put the lambda at the at the top here, the denominator. We usually do like that, and the epsilon naught we here write it at 4 pi k. Okay, make it look better. And the 4 cancels with the 2, the pi cancels with the pi. We get 2k lambda over r. I'm gonna here write that. 2k lambda over r. Which, by the way, is the same result that we got in the previous example. Let me see if I find that for you. Let's see. Not using Gauss's law, but using Coulomb's law, and going through the trouble of integrating it. I'm going to spend a little bit of time just looking for it. If I cannot find, we'll just keep on moving on, okay? Constant, it must be this one here. No, this one is not, the one. Let's see. Maybe it's the previous one. Let me look at the slides here. That's Gauss's law. We did for this one. We did only for this one, huh? We didn't do for, okay, yeah, we didn't do for the other one. It's possible to repeat this problem here, but calculating the electric field, not at this point, but at a point somewhere here. Okay, if you do that, we get this exact same result. So I didn't do that. I didn't do that using the other method. So keep that in mind. This result here. Apply for, this is the result. This is the result for an infinitely long rod. Infinitely long rod. Okay. Note that the E field goes down with the inverse of the distance and not with the inverse of the square of the distance. Why is that? Well, this happens because we are dealing with an infinitely long rod. A finite rod. A finite rod would not behave this would not behave in this way. A finite rod would behave with the square of the distance, would go down with the square of distance, okay? Which would the field would be given by the inverse of the square of the distance, okay? But what you see here, even though it's a infinitely long rod, even though this result is for an infinitely long rod, it is still, which by the way, which in practice doesn't exist, does not exist, comma. It also applies for a finite rod at distances that are very small compared to the lengths of the rod. Okay? So let's say let us say a rod of length L has an electric field that behaves with the inverse of distance. 4 points that are at position R less than L divided by 10. That's how you should interpret it. Okay, even though we derive for infinitely long rods, this result here is applicable for finite rods, provided the distance to the finite rod is 10 times less the length of the rod itself. Okay, so remember, this is an approximation. So here we go. We can repeat that. Let's go down. Any questions about that? Okay, we can repeat that for uniformly charged rod, just like we did for uniformly charged sphere. Okay, here's my rod. I can replace this rod with an actual rod. Let's see here. Here you go. I'm going to replace with this one here. Like that. And I'm going to do a solid, the dashed one, but a solid. Here you go. Okay, and it's not going to be Q rho, it's going to be Q sigma, because that's, oh no, it's Q rho, it's okay, because it's a solid cylinder. Leave like that. Radius R. Okay, let's put radius R here for this. I'm gonna radius R, charge density rho. And then here we have the case of a cylindrical shell as well. Okay, case of a cylindrical shell. Here you go. Put it here. How am I gonna do that? Let's see here. I'm gonna do like that. Single cylindrical shell. This one. Okay. Like that. Okay, that's the cylindrical shell. You can do for both of them. For the cylindrical shell, inside the shell is 0, the electric field is 0. And outside the shell is just like that value that we got, which is the inverse of the distance. For the cylindrical uniformly charged cylinder, inside the cylinder is going to be one result. Outside the cylinder is going to be the same result that we got before. Okay, we can do that. Let's do it for this one, but let's do just for inside the cylinder. Okay. So here you go. Going back here. What time is that? 5:41. Infinitely long cylinder with uniform charge distribution. Cylinder of radius r and uniform charge distribution rho. Like that. Let's do just for inside. Okay, so the procedure is similar to what we had for the, not the spherical shell, but for the let's see, yeah, that's good. You know what? Let's see here. Let's get this one. Oh, that's a spherical shell. I don't want the spherical shell. I want this one here. Here we go. Uniformly charged cylinder of charge density rho and radius big R. Symbol. Okay. We're gonna use the same thing. Here you go. Q enclosed divided by epsilon naught. But now instead of lambda L is going to be, let's see how I'm gonna do that. Is going to be, it's not gonna be lambda, it's gonna be rho. Rho. Rho times the volume. Okay. Gonna do the drawing for that. Let's do a drawing for that. We are doing, here you go. We are going to get, let's see if I'm gonna do that. You know what? I'm gonna use the other drawing. Here you go. I'm using this one right in here. This one right in here. Let's use this one right in here. I did for the sphere, but it can also be applied to the cylinder. Many of the drawings I can repeat them, can reuse them. Here you go. Okay, so here's my cylinder. Okay, here's my cylinder along the z-axis. You can even build radius r, and here's the Gaussian surface. This cylinder, the cylinder is infinitely long, but the Gaussian surface has a length L. Okay, so this Gaussian surface is going to have three surfaces just like we saw before. Okay, the actual cylindrical surface and the caps at the end, at the extreme. Okay, so let's go and let's okay, here you go. The cylindrical surface plus the caps. Cap and cap. And what you end up getting here is rho v. And by the way, rho v can be written down. Oh, I'm gonna do that right in here. The volume of that cylindrical surface is gonna be pi r square L. Okay, remember that's the volume of the cylinder, of the Gaussian cylindrical surface. So I'm going to copy that and paste it here. Okay, 1, 2, 3 surfaces. Just like before, the electric field here at surface 2 and 3 is going to be 0 because the electric field is perpendicular to the area vector. And we are left with this integral along. What changes is the right side. It's not lambda L anymore, but rho pi r square L. The electric field is going to go outside the integral, just like before, because the electric field over this surface here, the magnitude of the electric field over this surface is the same. The area vectors are parallel. And now we have this integral that we have to worry about. Okay, this integral is going to be given by 2 pi RL, because it is a cylindrical surface. The difference is what goes on the right side. The difference is what goes on the right side. 2 pi r, 2 pi r, let's see. Yeah, 2 pi r L. Good. Okay, so the surface, the cylindrical surface looks just like that. I'm gonna copy this one, and I'm gonna draw here for you so you can understand better. Okay, here is the drawing for here go, and I'm gonna do the following. Here go. I'm gonna get this cylinder and I'm gonna place it there. It has to be greater than the surface. Okay, did you get the idea? Okay, this cylinder is infinitely long, but not this surface here. This surface, this imaginary Gaussian surfaces, has a length L. Okay, see the A2 vector here perpendicular to the field, right? That's what we get. Surface 1, 2, and 3. It's not a rod anymore, so it's a actual cylinder. Let's finish our calculations. Notes. Now we are left with that equality on the right side. Okay, the L cancels out with the L. The pi cancels out with the pi. And the r squared cancels out with the r. We are left with this result here. Okay. Inside the cylinder, the field increases linearly with the distance. That I'm gonna put it here, R less than big R. What time is that? 5:50. Yeah, let's take a break here. But first, let me get your attendance. Any questions about that? So it's much. So if you use Gaussian, the Gauss's law, it's much easier to calculate those electric fields. That's the bottom line. Let's see this one. No. Huh. This one. Yeah, this one. Let's see if I got it. Oh gosh. No. Huh. Physics 38. Lecture must be this one. Okay. No. Okay, 24 should be 24 here. Okay. Sales left. Now, next, today is the 1st of March. Yeah. This one goes here. Now, Mario Acevedo. Are you there, Mario Acevedo? No. Toby. Are you there, Toby? No. Harum? Musa? Genesis Bell? Jennifer Camarillo? Nope. Faust? Robert Faust? There. Pedro Flores? Pedro Flores? Okay. Lawrence Flores? Okay, next. Alexander Garcia? Sung Hama Han? Brian Nis? Athena? Nope. Dylan Martinez? Rafael Mercado? Let me pause my recording here. Remind me to. We're back here, right? So here you go. We did for a cylinder, for the electric field inside the cylinder. To do the electric field outside the cylinder, we have to expand, we have to use a different Gaussian surface that has a radius greater than the radius of the cylinder itself. The final result for the electric field is going to be the inverse of the distance, 1 over r. But the constant that goes at the top is going to be different than that one that we got for the one-dimensional rod. Okay? But the important thing is the functional dependence on the distance. For the uniformly charged cylindrical rod, the electric field inside is going to be 0. The electric field outside is going to change with the distance, with the inverse of the distance as well. Okay? So what you're going to do now is this one here, which is the experiment that we did at the classroom. We're going to apply the Gaussian surface to an infinitely long sheet, planar distribution of charges, infinitely long planar distribution of charges. Okay? If you want to have a gut feeling of how the electric field of this charge distribution is going to look like, okay? You can do what I did here, okay? You can go ahead and, here you go, get the infinitesimal contribution from this little charge that we have at this spot, the dq, right? And you're going to get an electric field that goes like that. you do the same for this other spot, you're going to get an electric field that's going to go like that. Notice that we end up, in general, getting an electric field that's going to be on the horizontal, unless we are approaching the edges. Remember, we are doing that in a qualitative fashion, okay? And doing that in a qualitative fashion is okay, because you have to have a qualitative idea of how the electric field is going to look like, okay? So here you go. In this case here, at the edge, nearby the edge, you're going to have an electric field from this very edge that's going to point in this direction. And since there are no electric charges here in this region, we are not going to have any electric field contribution from that. But we are going to have electric field contributions from this very edge here that's going to point somewhat like that. Okay? So nearby the center of this planar distribution, the electric field is going to be quite in the horizontal direction, but nearby the edges, you're going to have what I mentioned to you before, what is what we call the edge effect. Okay, we're going to have something like that. The net field is going to be somewhat like that. But nearby the center, no, nearby the center is going to be almost in the horizontal direction. If we go ahead, do the same for a point nearby the other edge, the lower edge, here you go. So the electric field of this point is going to be somewhat like that. That's what we call edge effects. I'm exaggerating, okay? At this point, you wouldn't be like that. It would be a little bit more closer to the center. So keep that in mind when we start thinking in terms of electric field. It is okay, like I said, for you to have a qualitative idea of what would be the electric field of a given distribution of charges, okay? If you want to know exactly what's going to be the electric field distribution of a given distribution of charges, then you have to apply Gauss's law, or you apply the Coulomb's law and integrate the whole integral, okay? Now, let's take a look at how we will apply Gauss's law to this type of charge distribution. I'm going to erase that. Okay? Okay, what we do here, if you have a very large planar distribution of charges, we can say that this planar distribution of charges has cylindrical symmetry. And so what we do, we use a cylinder, a Gaussian cylinder like this one, to find out what's going to be the value of the electric field. Just like before, this cylinder has three surfaces. I, call this one the cap, surface 1, this other cap, surface 2, and then cylindrical surface 3. Okay? Here are the area vectors of the cylinder. Let's break it down so you don't get overwhelmed. Right, here you go. First, let's start with the cylinder itself. Okay? Then we come up with the area vectors. Oh, wait a minute. I'm gonna get another one here before I lose this work. Here you go, cylindrical surface, and come up with the area vectors. I call this vector here A1. I'm gonna make it larger too, otherwise it's difficult to see, right? You know what? Before putting the vector, let's instead call it the surfaces. That's better. You know, I put the vector afterwards. I'm gonna name the surfaces first. Here you go. This surface is 2. The surface to the left is 2. I'm gonna call this surface to the right 1. And this cylindrical surface 3. And now I'm gonna put the vectors there. Vector A1, vector A2. Oh, oops. That's vector A. Oops. One more. And now I can paste it there. Okay, here you go. It's too small for me. Let's get this guy here. Larger font. Here you go. Yeah. Yep. Here you go. A1. Right? The next one is going to be A2 here. And I'm going to get this, make it longer so you can see it easier. And the other surface A3. Here you go. What else do we have to know? Well, we have an idea that this electric field points to the right. Remember? Here you go. We have an idea that the electric field is going to point from in the horizontal direction. By doing that simple I'm gonna put it here. Here you go. I'm gonna get this guy to A3 on the other side as well, just to emphasize that's the here you go. The electric field here is perpendicular. This guy, right? I don't need this one here. And I can come up here with this one of these fields. Qualitatively speaking, we know that the electric field is going to be in this horizontal direction. And remember, we are talking about infinitely large plate. Here you go. So now we go ahead and do our integration. Infinitely long plane, okay? Infinitely long, infinitely large planar surface. Just like before, we are going to have three surfaces of uniform. Oh, don't forget uniform charge density, right? Infinitely large plane, infinitely large planar surface of uniform charge density sigma. Font. Here you go. Q enclosed over epsilon naught. And then here you go. What I'm gonna do here, I'm gonna put sigma area. Sigma area. Don't forget, we have a closed surface. Oh boy, I forgot my... Thank you. Let me get my mask here. Don't be ashamed of reminding me that, okay? It looks like I forgot my shield there upstairs. Let me get my shield, okay? Here you go. Prefer to use my shield. Here you go. That's what the Q enclosed is all about. The surface charge density times the area. Okay? And now I'm gonna break it down, this integral, into three surfaces. I already did that. Surface 1, 2, and 3. And I'm gonna do something else too. I am going to tell you that this cylinder has a radius lowercase r. Okay, let's see how I'm gonna put that. Here you go. Like that. Oops. Here you go. I'm gonna make it dark and thicker as well. Here you go. Surface 3. I'm gonna move this 3 here somewhere else. And I'm going to make it R, okay? And now that I told you that the radius of the cylinder is R, I can write down that the area is going to be pi r squared. Okay. I worked out the left side and I worked out the right side. Let's go for the next. So here goes surface 1, 2, and 3. Okay, surface 1. Here you go. Here's the surface 1. From that original derivation, we got this qualitative result that showed to us that in the bulk of this plate, the electric field is going to be in the horizontal direction. If the plate is infinitely large, the horizontal direction of the electric field is going to be everywhere. I just do not know how it decays as time goes, as the distance, as you increase the distance further and further. Okay. So, because of this simple, this rather simple analysis, we can say that the electric field here at cap 1 is parallel to the area vector A1. And same thing for the cap number 2. Okay, so for surfaces 1 and 2, that integral becomes simpler. Surface 1 and 2, we get, E dot dA is going to be magnitude of E times magnitude of dA. I don't even have to put, like I said, that one there is redundant. We don't need that because the electric field is still inside the integral, okay? 1 and 2. Here we go, 1 and 2. Good. What about surface 3? Let's go back here to surface 3. For surface 3, the electric field is perpendicular to the area vector, whether it's on the left side, whether it's on the right side. So the third integral is going to be 0. It's not the integral that's 0, but it's the dot product inside the integral that's 0. Right? It's even better than that. So now we have, it's kind of similar to what we did for the linear charge distribution, right? What's the next step? The next step is the following. Is to recognize that the electric field over this cap is going to be, the magnitude is going to be the same, because they are both 1, 2, and 3 at the same distance from the charge distribution. That's the next step. Okay, the magnitude here over the surface is going to be the same, so we can do the following. We can take this E outside the integral, and it becomes, because the E is now outside the integral, now we should put the subscript E1. We do the same for the other one, the second cap. Okay, but don't forget, here you go, the electric field on the second cap. We don't need this term anymore. Now we go the next step. The next step is to calculate the area over surface number 1. Area over the surface number 1 is pi r squared. Okay. we go pi r square. Over the surface number 2 is also pi r square. Okay, and then we go the next step. We recognize that the pi r square cancels out. Pi r square on the left side cancels out with the pi r square on the right side. And now we finally, finish the problem. Right now I have only magnitude of 1 plus magnitude of 2 is equal to sigma over epsilon naught. What I do the following. Look, folks, what I'm going to do, I'm going to get a distance of this cap to the plate that is the same distance. So from here to here is going to be x. From here to here is going to be x as well. Okay? Choosing, so we can choose. Choosing cap 1 at the same distance from cap 2 with respect to the charge distribution, comma, we can argue that the fields at these positions, at these two positions, are the same because the magnitude, not the fields, but the magnitude of these two fields are the same. Because, okay, we go, zoom out. Well, because they are the same distance, right? Same distance from the source would generate, in other words, same distance from the source results in same magnitude of the field. So in other words, I'm making E1 equal to E2. Okay, so here you go. Magnitude, in other words, E1 equal to E2. And now I'm going to rename them E. Oops. Go like that. Like that. So next, E1 plus E2 is equal to 2E. We solve 2E, not QE. 2E. We solve this equation. We get E equal to 2 epsilon sigma 2 epsilon naught. Is that what we got before? We did for the plate, right? Go. Let's see if we can find the result. Should have been around here. Let's see here. This one. No. Disk. The field summary is that solution along the x-axis. Is that the one? A disk, okay. Net charge Q. So let's see here. X sigma blah, blah, I did for r much less than x, and then I did for r much greater than x, right? R much greater than X. And then, okay, that's what I got. Here you go. 2K over R squared. Let's see how this 2K over R squared compares with what we got here. Okay? 2KQ over R squared. Okay, from previous result of a for a disk, you know, a X much less than R, we got the following electric field. We got something like that. Okay? This result should reduce to this one here. So let's see if we can do that. Okay? Let's not forget that R is the radius of the circle and Q is the charge. Okay, so the question is how to reduce this result to the previous one that we used Gauss's law. Okay, well, not gonna be that difficult. Okay, notice that we have epsilon naught here and we have K here. So the first step is to translate my K in terms of epsilon naught. Okay, that's the first step. And then we do the rest. And then we worry about the rest later on. Here you go. K becomes 4 pi epsilon oh gosh, epsilon no epsilon okay, not. That's the first step. So let's the K no longer here, right? So let's simplify as much as we can. 2 cancel out with the 2 downstairs, right? Becomes 2 pi epsilon naught. Okay, we are in the right direction, right? It looks like we are in the right direction because we have 2 here. We have epsilon naught here. We have 2 epsilon naught here, but it didn't quite get there yet. Note that pi r square is what? Pi r square is the area of your disk, right? Is the area of your disk. And finally, what? Q over A is what? Q over A is nothing but sigma. Okay? Is nothing but sigma. And what we got using a previous technique matches with what we got using the Gauss's law. Okay? Save it. One more. What time is that? 6:45 already, huh? Let's see if we have any other one that we can do quickly. Okay, yeah, here you go. Here's the circle, right? I didn't show this drawing, but here is the radius of our yeah. I hate when those things happen. Let me see if I can just copy what I had before. Here you go, this guy that I want. You can hardly see that radius, right? Here you go. Now we got it. And this guy here, let's see if I can oh gosh. Okay, you got the idea. Okay, so here you go. that's what we get, not for a positive charge, but a negatively charged distribution. Okay. Fix that, right? And then we did that before, right? If we put two plates next to one another, this one's negatively charged. Okay, outside this charge distribution is gonna be 0. Inside is gonna be twice what we got. We go. Go. I don't need that anymore. We go. Yeah. Yeah. Some time ago, I was replacing negative with positive, and I didn't notice that I ended up replacing the wrong negatives with the positive. Okay. So here you go. That's what's all about. More. Okay, so what time is that? 6:48. Okay, we can go meet outside, upstairs. You know, and I'll see you soon. Okay. Oh, that was the experiment that we did, right? See that? That's the experiment that 13579. See that? Most of you must have seen this edge effect right in here. If again, if this plate extended very far away, all those lines here, equipotential lines, become parallel. And I got to fix this guy here. We go. Let's go. So I see you upstairs.